what I'm going to, well, first, as everyone else has done, let me acknowledge the efforts of my co-authors, which include Josh Cahill, Keith Rainey, Ben Bussey, and the MiniRF team. And the MiniRF team is not a large team, but certainly pretty much everybody associated with the team has contributed in some way to what I'm presenting today. And what I'm going to present is an application of some data products from the MiniRF radar instrument. So I'll give the obligatory slide on the MiniRF instrument to begin with. It's a hybrid dual-polarized, side-looking synthetic aperture radar. It transmits at two frequencies, S-band and X-band. And it operates in two modes, a baseline mode with a resolution of 150 meters and a zoom mode with a resolution of 30 meters. The products I'll be showing you today will be from S-band zoom. So they'll be at about 13 centimeter wavelength, 30 meter resolution. The measured return signals, MiniRF measures the return signals in two orthogonal polarizations that allow us to compute the 4 Stokes parameters from the radar data. And these are important because from these parameters we can create a number of useful products for looking at the surface of the moon. So just to show you what the calculation of these Stokes products looks like, these are the 4 Stokes parameters. We have a 4-band cube that comes down from the radar instrument with the two orthogonal polarizations and their real and imaginary components of their cross product. And so S1 here is going to be essentially the total power returned by the radar. Okay, so it represents the addition of the horizontal and vertical polarized components of the return signal. And what I'm showing here is basically a map of half of our coverage of the entire surface of the moon at a center longitude of 240 degrees orthographically projected. So Oriental Basin is right here. Okay, and this looks very gray. Well, you know, this is just a typical radar image, but we can make it look nicer than that. We can create one of the derived products. This is very commonly used to derive product in ground-based radar data for the moon and radar data in general. It's the circular polarization ratio, Scpr, and it represents a ratio of S1 and S4, the first and fourth Stokes parameters. It's an indicator of surface roughness at the wavelength scale of the radar. So remember, I said we're looking at about 13 centimeters. We can be sensitive at this wavelength to roughnesses in the centimeter to meters range. So anything that's rough in that range shows up in the radar. And what shows up especially well are young, fresh craters because of the ejecta deposits, the blocky ejecta deposits associated with them. So, you know, again, now here's Oriental Basin, shows up much more clearly when it's represented by CPR. And we're looking at the lunar far side. You can see in general it's rougher than the near side, which is off toward the terminator here. What I'll mainly be talking about for this talk is one particular crater, Burgess A, found right here east of the Oriental Basin. And I'll be talking about it in the context of both CPR, looking at it in its roughness characteristics, but also looking at it using a product that we have more recently developed for use with MiniRF radar. This is not something that's been used with ground-based data of the moon. It has been used with terrestrial radars looking at Earth. And so we've tried to take that application from Earth-based radar and use it for our lunar radar. And it's the Mkhi Decomposition. So basically we're decomposing the total power, or the first Stokes parameters, into its scattering components. So what you see here are the equations for an RGB image where essentially green represents the portion of the signal that is depolarized. And red and blue represent the portion of the signal that's polarized and separates it into the direction in which it's polarized. So red is even bounces, represents even bounces returned from the radar. Blue represents odd bounces. So, you know, because most commonly it would be a double bounce or a single bounce, that's what we call it, but technically it could be 3 bounces and 4 bounces. You get my meaning. And then, so you can see here some differences between CPR. You know, we still are sensitive to roughness. This is still looking at blocky materials, but it doesn't show up. The lunar highlands certainly don't show up as bright as they look in the circular polarization ratio data. So like I said, I'm going to concentrate on one crater in trying to show you what application we can use, how we can use the Mkhi data to give us some valuable information about the lunar surface. This is Burgess A. This is an LROC WAC image of Burgess A, centered right here in the middle. It has very extensive and bright ejecta deposits. Burgess is right here. It impacted the rim of Burgess. And if you were to draw kind of a generous, probably, circle around what would be continuous looking, this certainly doesn't represent the continuous ejecta blanket. It represents more than the continuous ejecta blanket. But we can see that bright ejecta appears to generally fill or lie over the lunar terrain within this circle. And one reason I drew this somewhat generous circle is when you look in Scpr, the circular polarization ratio, you see an increased roughness associated with everything within this region, indicating that we're observing the ejecta. At the wavelength scale, we're seeing blocky material out to a distance of about 7 crater radii, about 70 kilometers. This is a 20-kilometer diameter crater, and we're seeing enhanced roughness of the surface out to a distance of about 70 kilometers. And then you still get enhanced roughness further than that, but it starts to show up as rays, not as a generally continuous deposit. So when we look at it with Mkhi, we see something slightly different. We do see a signal indicative of rough deposits that represent essentially the actual continuous ejecta blanket of the crater. And then we don't really see much beyond that. We see indications of volumetric roughness, and I should point out, here, I'll point out these scales. Here, CPR, it's a ratio. It goes generally from 0 to 1. We can see CPRs higher than 1. And in some cases, that could represent deposits of water ice. But there are blocky deposits that can give you CPRs higher than 1. For Mkhi, again, we're looking at an RGB image. So combinations of colors represent combinations of scattering properties. So when we see yellow, it's generally a combination of volumetric scattering and double bounce backscatter. Double bounce would represent very blocky material, or again, it could represent volumetric deposits of water ice. If you saw Ben Bussey's talk in the other room a few talks ago, he would go into more detail about that aspect of what the radar could do. I'm not concentrating on that. I'm concentrating on how we see blocky deposits with Mkhi. Bluer regions represent primarily single bounce backscatter and some combination of volumetric scattering. And I'll show you some squiggly lines in a minute. I'm a geologist, but I can actually am using some squiggly lines here in this radar talk. And so the idea is, okay, we produced this Mkhi. Let's see what it can tell us about the moon that maybe CPR can't. And in order to kind of motivate what it can do for us, I'm gonna not show you Burgess A first, because that's the interesting thing. I'm gonna show you something less interesting that kind of calibrates what we should be thinking, or how we should be thinking about things. I'm going to show you a much smaller crater, but a very young, fresh crater to the northeast of Burgess. So what I've done is I've taken a small subset of that mosaic I showed you of our data. On the left is the circular polarization ratio. On the right is the Mkhi decomposition of this area. This vertical line through each represents this horizontal profile through each, and forgive me for all this. The horizontal line here represents this vertical line. The reason I put one there is I'm trying to show basically where the edge of the ejecta blanket of this particular crater is with respect to the lunar background regolith. Right. So beyond north of this line, we're really only seeing lunar regolith. Whereas below that, up to, I guess, this point right here, we're seeing crater ejecta. And if you look in the CPR, you definitely see, and forgive me, this is a little bit noisy, but you can see the general trend that once you get to the ejecta blanket, CPR increases by a fair amount until you get to the other side. And then you end up with a lunar background, lunar regolith CPR value of about 0.4. So if you're seeing a CPR of about 0.4, you're probably seeing lunar regolith. Lunar background terrain. Now, when you look at the Mkhi, and I hope you can see some of the differences here, when you look at the various RGB components of it, what you see is the lunar background is actually generally a combination, almost equal parts, volumetric and single bounce backscatter. Very low double bounce backscatter observed. When you get to the crater ejecta, you see an increase in volumetric scattering. That makes sense. You also see a decrease in the proportion of single bounce backscatter. I'll speed up then. And a slight increase in double bounce as you get into the crater, which makes sense. Again, you're seeing blocky materials. Okay, so having calibrated ourselves to what we should expect to see, I'll show you a region of Burgess A. This is Scpr. This is also what we expect to see. We're seeing roughness deposits associated with the crater ejecta. Unfortunately, with this mosaic, we don't get very far into background terrain until we get much further through the mosaic, and that would have made this profile very long and very hard to view, so I cut it off a little. But you can see the increase in Scpr as we go across Burgess through the crater and to the other side. When you look at Mkhi, we definitely see the crater as in a very similar manner to which we observed that smaller one I just showed you, beginning about right here where the continuous ejecta blanket is observed in Mkhi. You're going to see this increase in volumetric scattering, a decrease in single bounce, and an increase in double bounce. But again, the ejecta blanket, as seen in Scpr, we see roughness indications for the ejecta blanket much further out. It's difficult to observe probably from where you're sitting. We do see an increase in volumetric scattering in that region. So as you get out to about background terrain here, you see that kind of equivalent single bounce scattering to volumetric scattering, and we definitely see an increase that begins where we see the Scpr indications of the ejecta blanket. But we don't see that drop in single bounce or that increase in double bounce until we get to the continuous ejecta deposits. So I've pointed out that out here. I've separated it into about 3 regions. Our working hypothesis, well, it's really simple for region 1 and 3. Region 1 appears to be the scattering signature of crater ejecta. The third region I have highlighted here appears to be the scattering signature of lunar regolith. Our working hypothesis is the scattering properties of crater ejecta and lunar regolith are being observed in this middle region, and that suggests the thickness of the ejecta is less than the penetration depth of the radar signal. So basically, we think we may be seeing through the ejecta deposit into the lunar background terrain. So why is that important? Well, the thickness of the ejecta for Burgess A at radial distance is greater than 10 kilometers from the crater rim is on the order of meters if our working hypothesis is correct. But various authors from way back when in the 70s, Mkhi and Pike, predicted ejecta thicknesses much larger than that at that radial distance from Burgess A. So what we may be seeing is, first of all, what we may be getting is a hard constraint on ejecta thicknesses at a given distance from the center of a crater using the radar data. And this also may be allowing us to inform models for ejecta thickness and ejecta emplacement on the moon. These models were developed from basically experiments on the ground and field work that it looked at craters on the surface and craters produced by nuclear explosions. So, there's not been a whole lot of direct evidence for ejecta thickness of the moon, maybe until now. So future work, we've identified 22 additional fresh young craters because n equals 1 is not satisfactory in most cases. And we've found them in both highland and Mare terrain. These are all Copernican craters. They're fresh, young. We should be seeing very similar characteristics if this hypothesis turns out to be correct. And we're looking forward to reporting on you at future meetings as this work progresses. So thank you. Yes.
Maybe an alternate is that what you're seeing is the interface between early ejecta and late ejecta, and that there's a sorting difference between the sizes of those two regimes, because I know clearly from looking at the NAC data that over and over and over again on these Copernican craters, you can see that there's distinctly 2 different types of ejecta, one early and one late.
Yep.
And the fact that you're getting such a different estimate for the thickness of those ejecta probably means you're wrong.
It's very possible. But, and we definitely thought about the fact that you might be seeing different sorting. They might be seeing 2 different types of ejecta. What's still interesting to us is that in the Scpr, we definitely observe the roughness at the wavelength scale of the radar. It's lower, but we observe it. So if the sorting was such that you got a much different distribution in size of the scatterers, we might expect that it would not appear in the radar data. But we're definitely going to take a look at that. We have some X-band data of some of these craters as well, and we're going to try to get that involved and try to see if that is indeed what we're seeing. So it's I said a working hypothesis. We did have another idea in mind, and you just highlighted it, and we'll see what bears out.
One more question.
I'm curious, why did you showed two craters? The first crater didn't show this effect. Why?
Yes.
Why do you suppose that crater was different?
Another good question.
This crater was different.
Yeah, I think part of it could be if you're looking at gravity-dominated versus strength-dominated targets. There are definitely differences in the scaling of ejecta, how thick it is and how far it goes based on those two regimes. But it's one reason we've chosen craters that fall on both sides of the strength of gravity dominated for the moon, so that we can see that effect.